Hi, my name is Jason, and I'll be presenting my part of our group submission for the PYJAC 2022 hackathon. And so for my part of our project, I've chosen the prompt of designing an interactive game. And this is a beginner prompt, although we are competing in the intermediate category. And so my program basically simulates the collisions between particles inside of a box, and all of these collisions are modeled as perfectly elastic. So let's press the random button over here, and we're going to end up with a random set of particles that are each of different speeds, different sizes, and different masses. The particles collide elastically off the sides of the container and with each other. And the slower particles are bluer, whereas the faster ones become more and more reddish colored. We can clear the screen, and we can also add particles one by one. So we can control the speed, the size, and the mass of the particles we use, the particles that we add using these buttons over here. So let's add a really small, really slow particle. Do-do. We can add more, and let's spice things up and make a really fast particle. There we go. And let's add a really fast, really big particle. And let's add another one just like that. And when we get tired of some of the particles on the screen, we can remove them one by one using the remove button. But of course, if you're too lazy to go out of your way and just design all these particles yourself, you can just press the random button and you can have a random collection of particles appear on the screen for you. And that's all there is to it.
Good day to those who view this video. PYJAC judges all. The purpose of this part of the project was to construct a Python implementation of the well-studied Wiener process. This is a real-valued stochastic process considered to be synonymous with Brownian motion due to serving as a stochastic or probabilistic model for the one-dimensional case of Brownian motion. While my groupmate would have worked on connecting an intermediate and beginner prompt in both computationally and replicating a famous physics experiment, creating an interactive game, this part of the project focuses on simulating a random walk to explain the natural phenomenon of Brownian motion, as seen here. So, as I've already defined the Wiener process, the first thing done, aside from importing NumPy and matplotlib.pyplot, was to define a function that would generate three-dimensional Brownian motion from a random walk process implementation. The random walk in question that generates the Wiener process, in this case, has three options, where the particle can move either one unit parallel or anti-parallel to the unit vector, or remains constant with respect to the unit vector. The unit vectors in question are the conventional unit vectors of Cartesian space, which is the x-hat direction, the y-hat direction, and the z-hat direction, standard basis. So the Wiener process is generated from the lattice random walk here, and the movement of the particle is stored in an array x, y, and z. No, well, stored in arrays x, y, and z. So one-dimensional Brownian motion is the second part. Well, the second part of the project involved the plotting of one-dimensional Brownian motion, two-dimensional Brownian motion, and three-dimensional Brownian motion, generated from a random walk of 1,000 steps, and thus the pattern was defined over 1,000 steps. I can run the code. Here we get patterns, one-dimensional, two-dimensional, and three-dimensional of 1,000 steps. And it should be noted that the patterns generated are truly stochastic and not at all deterministic, as is the case with Brownian motion. Well, yeah, because Brownian motion is not deterministic, it's truly stochastic. We can run it again and show that we get different patterns, and I can run it again. Just for the sake of things, yeah, and show that we get different patterns. It has the characteristic shape of a Brownian motion pattern, and I go into a bit more detail as to why we could use the binomial process of a random walk to generate the Wiener process here, but the video will get too long, so I'll just leave it to when you read it. Alright, thank you.